In this video, I'm going to talk about line integrals with respect to a particular direction like x or y. What do I even mean by this? So I want to go back to our first introduction to line integrals where we talked about some scenario like this. We would have some curve along the bottom that often could be parameterized as r of t. It might have two different components, say g of t in the I hat and h of t in the j hat. And then we had some height above this curve, and as long as the original curve was two-dimensional, one interpretation for the line integral was that it was the surface area that was formed, the surface area of this particular image. So that was the old line integral. When the curve was three-dimensional, then this exact sort of geometric interpretation didn't work out so nice, but there are many points that we've seen where using a line integral was very useful. However, to actually compute this, we use this larger formula. This is a formula that respects the specific choice of parameterization that we have with the g of t and h of t's. So anyways, this is the scenario that we come into this video with. Now I want to do something different. Imagine you're standing at y equal to, I don't know, minus infinity, way down on the negative y-axis, and you're taking a flashlight and you're pointing at this thing. Then imagine that there's a wall at the xz plane, and you take a flashlight and you point it at this, and what you get is the following shadow. You get this sort of projection of the curve onto the xz plane. That's what I've done. So the question then might be, well, what is the area of that projection? Effectively, what's going on here is that I want to do a line integral. It's just, I don't care about the contributions from y. As it changes to y, that's sort of irrelevant. I'm only interested in the contributions from changing the x value. And so that's really what we want to capture with the notion of a line integral with respect to just, in this case, x. So that's what we're going to do, the line integral with respect to dx. And then the symbolic change that I'm going to make here is that I'm going to do the integral over a curve of some function, but instead of writing ds, which is what we previously did, we write dx. I haven't defined what I mean by this yet, but this is what I'm going to define notationally. I'm integrating not with respect to ds, but instead just in terms of dx. And loosely, when we thought about what arc length was, you change your arc length a little bit, you can make some changes in the x and some changes in the y, and your movement is a combination of both of those. And I'm saying, I'm just adding up. Integrals are just adding up things. I'm only adding up the contributions from the changes of the x. Okay, so then if I plug in my specific parameterization, what I'm going to get is the same type of thing I've seen before. The f is evaluated at g of t and h of t. But the stretching factor is now just g prime of t dt. Indeed, before what happened to this spot, remember it was a square root of g prime squared plus h prime squared, the x component and the y components. This is what was happening when we were considering that both. But basically what I'm doing here is I'm just ignoring the h prime part. I'm just assuming it's zero. I'm saying I don't care about any contributions from the y part. And when you take a square root of a square, you get back to the original. Or, well, perhaps you get back to the original with an absolute value sign. When we talked about arc length, we really wanted to think of arc length as an intrinsically positive concept, so it was okay that it had absolute value. But maybe I want to be a bit more general here, and so I'm just going to let g prime be positive or negative. Either way, this is what I'm going to be computing. That is my line integral with respect to dx, and in this example, it represents the surface area of that projection onto the xz plane. Now, notice already, if I was to project onto, say, the y-x plane instead, and do a line integral with respect to y, which you can absolutely do, it would lose this geometric meaning because when you compress along the y, you notice that there's overlaps. Maybe you'd have to break that into multiple different regions and do some adding and some subtracting if you wanted to be careful about the signs. Anyways, the point is you can do a line with respect to x or y, but you have to be careful about what it would actually mean. So ultimately, if you know your parameterization, which means you know your g of t and your h of t, you just plug into this formula and you get your answer, at least up to your ability to do that integral. Now, as you will recall, we upgraded from just the normal generic definition of a line integral to the more specific case of a line integral of a vector field. So if I now pop up some vector field here, I want to figure out what would be the meaning of a line integral with respect to just x or just y of a vector field. Well, in my example of my vector field, my x component, my I hat direction, has coefficient function m, and in the j hat direction, it's got coefficient n. So what I want to imagine is if I only care about what's happening in x, I do not care about the movement in y at all. It's sort of the same thing as just saying, well, let's just zero out what happens when it's y. Let's just make n equal to 0. So in other words, I get this new vector field. It's the same m I had before, but just 0 in the j hat direction. Well, this can come up in all sorts of things. Imagine, say, you're studying aerodynamics of a wing, and you have some velocity field that's capturing all sorts of motion. But if you're talking about a wing, you might not care about the motion of air which is happening tangential to the wing. You might be interested in the portion that's happening normal and can maybe construct some sort of lift to the wing, whatever else. And so you might care only about what's happening, the effect of this field in one of those directions. And so you get this kind of thing where you just zero out the other component just because you want to ignore it. Okay, so let's talk about line integrals with respect to fields this way. I have my generic field with an m and an n component. I have my generic curve here with a g of t and an h of t component. By the way, the exact same thing works in 3 or any other number of dimensions. I'm just putting it up for 2 dimensions right now, but you can just add a k hat component if you like. Then what we've seen previously is that the line integral of the function along the curve is just given, well, symbolically as the integral along the curve of f dot t ds. Indeed, this was precisely what we talked about in our introduction to line integrals of vector fields. And indeed, we'd seen a way to compute this when you put in the specific parameterization with the integral from a to b of f of r of t dotted with dr dt dt. The right-hand side was how you computed it if you had a specific parameterization. Now, let's actually do this. I mean, f has 2 components. R has 2 different components, and R prime, the derivative of R with respect to t, has 2 components as well, g prime and h prime. So if I actually just compute this out, what you get is m times g prime, that's the I hat components multiplied together, and then n times h prime, which is the j hat components multiplied together. The integrand has a sum. I could then just replace this as the sum of 2 different integrals, so an m times g prime dt and an n times h prime dt. And these are going to end up being my line integrals with respect to x and y, respectively. Indeed, the g prime dt, this is just going to be labeled dx. The idea is that when you change t by a little amount dt, you get a change in x, but it's got a scaling factor, the scaling factor being g prime. And likewise, the dy I will define to be the h prime dt. Again, you change t a little bit, then with the scaling factor of h prime, you get a resulting change in y. All right, so these integrals are how you would actually compute what we'll call the line integral of a vector field with respect to x and the line integral of a vector field with respect to y. But it's helpful to come up with a little bit of notation. So I'm just going to shorthand it and call this the integral of m dx and the integral of n dy, just to have a nice shorthand view of it. Here, the left one is going to be the line integral of the field with respect to x, and the right-hand one, the same thing, but with respect to y. All right, let's see an actual example computing these. So the example is going to be, I have some curve. The curve is the parabola y equal to x squared in the plane going from 1, 1 to 2, 4, just some curve. And then I want to compute a particular line integral with respect to y. So the line integral I'm challenging you to compute is the integral on the curve of x over y, that's my integrand, and then dy. This example doesn't have any explicit mention of a vector field, so it's kind of like the scenario that we began this video with, but I could have given you a field as well, and you had to do your dot product and get this particular integrand. Nevertheless, we have to go and compute it. So first thing, step 1, is to parameterize the curve. Now this curve is a little bit funky, there's a bit of a trick for parameterizing it. Whenever you have a graph of a function, like you have y is some function of x, in this case, the function is x squared, then the standard parameterization is you set x equal to t, and then y equal to whatever the function of t is. In this case, t squared, because y is x squared. So anytime you have it explicitly written as a function, y is some function of x, just make x equal to t and y f of t. And note carefully here, I have to specify the limits of my t. My t is going between 1 and 2, and that matches going from the point 1, 1 to the point 2, 4. When you plug it in, indeed, you get that property. Next step, I want to go and take this parameterization that I have and substitute it into my integral. So I'm going to do an integral that's got many different components. So first of all, limits of integration are the limits of the t's, so the 1 and the 2. Secondly, well, the integrand is x divided out by y, and so I write t divided by t squared. And then thirdly, The dy, we have to recall what that is. dy is the same thing as h prime of t dt. So the h prime is the derivative of the y component. So the y component is t squared. Its derivative is 2t. And so I plug it in and get just 2t dt. This is an easy integral to do. The t's are going to cancel, just leaving with an integrand of 2. And then you evaluate that and you get the result 2. All right, so in this video, we've seen how to compute the line integral with respect to a particular direction, either x or y or z if you had more of them involved. And we've seen a couple interpretations of this in the simple case of a two-dimensional curve. We could talk about line integrals representing a surface area, in which case the line integral with respect to x was a projection. And then similarly, when we were talking about vector fields and we were talking about line integrals of a vector field, you could also ignore either the x component or the y component and zero it out and just take the line integral of a field with respect to one of the directions x or y, or if you wished, z. And these are extremely useful for when what you're trying to measure, what you're trying to care about is an accumulation in one direction and you don't care about what's going on in some other direction.